So we have our density functions for y. And this is for y in the range 0 to infinity. So here, x conditional y, x conditional y. This joint density function, we did x over y negative y over y, and divided by e to the negative y. So you get e to the negative x over y, and this is for x can take all values from 0. All right. So now we have our tangential function, our conditional density function, conditional expectation. It's going to be integral x times now, whereas our conditional density function is 0 when x is negative, so I have to only integrate from x going from 0 to infinity. X times, and the density function when x between 0 and infinity is this. Negative x over y. So here we have to integrate by parts. You have x e to the negative x over y, y here. When I integrate e to the negative x over y, I get negative 1 over y in the denominator, minus 0 infinity. This integral gives me e to the negative x over y, y times negative 1 over y. The derivative of x is just 1, so I'm just integrating by parts. And when I take this, evaluating at infinity, that's 0. When you plug in x equals 0, you get e to the 0, that's 1 times 0, so that's just 0. There's a negative here and a negative here, so that gives you plus. Your y's cancel, and you have 0 to infinity e to the negative x over y dx, negative x over y, negative 1 over y, infinity to 0, y e to 0, that's y. So our answer is the expected value of x conditional on y equals y is just little y. And as I said, when you take conditional expectations, the answer I get will be a function of whatever I've conditioned y to be. So if I ask you what's the conditional expectation of x conditional on y equals 2, the answer would just be 2. So either you can solve it for a general condition on y equals y, or throughout I can condition on y equals 2, in which case I'd find fy of 2 in this case, right? And right throughout, my y would be 2. So if my question had been conditional expectation of x conditional y equals some, if I give you a numerical value here, in all your calculations here, you can replace y, the y with 2. All right. To make a remark about conditional expectations. So conditional expectations satisfy all the properties of unconditional expectations. say, for example, recall some of these properties is just going to be A times the conditional expectation of this plus B. So if you recall when we did the expectation of a constant is just that constant. So the conditional expectation of constant is still just a constant. So for example, so this is one of the properties, but basically any property satisfied by expectation is also satisfied by conditional expectation. Another property would be if I'm interested in the expectation of not x but g of x. That again would either be defined as in the discrete case or g of x in the continuous case. Instead of talking about expectation of x, condition on y, I can talk about expectation of some function of x. So the same definition for expectation of a function is now used, but I've weighted with the conditional probability. Next, we're going to talk about the relation between unconditional expectations and conditional expectations. And sometimes conditional expectations are useful when you want to calculate unconditional expectations. And I'll give you an example next class where you'll see how conditional expectations can be used to calculate unconditional expectations. But let's first write down the relation between them. So computing expectations by conditioning. The most important example for computing expectations by conditioning is when, say, I have a random variable, let's see, which is 1, 2, like this. To calculate the expected value of z, supposing this was a random sum, okay? That is, I don't sum over a fixed number of random variables, I sum over a discrete number of random variables. So this y is random. In that case, the way to go about calculating the expectation of this term is you first condition on different values y can take, and look at the expectation of the sum condition on each of the values this can take. So basically, we will do this later on, but I just want to give you an idea of this. It's like, supposing y takes discrete values, I would look at the expectation of goes 1 to n xi conditioned on y taking the value n over all values that n. So this is just to give you an idea of why conditional expectations are important, because there is no other way you can calculate the expectation of this. You have to condition on what y is, and then once you've conditioned on that, then it's just a straightforward sum. Okay? So that's easy. All right. As I said, we'll do problems like that later. So here's a proposition that I'm just going to state and not prove. And that is, if I want to find the expectation of x, I look at the conditional expectation of y. So here is a condition on y. You saw in our earlier example, our conditional expectation, if I had conditional y taking the value little y, our conditional expectation was a function of little y. Supposing I don't say y takes condition on y takes a specific value, but what are conditioning on the value of y, your answer would have been capital Y. So it's the expectation of that. So you can think of this conditional expectation as a function of this y, whatever y is, you're conditioning on that. So conditioning on knowing the value of y, your expectation of x conditioning on y is some function of this random variable y, and we take the expectation of that function of y. And I'll write down what the formulas would be for the discrete and continuous case. That is, in the discrete case, I'm saying what I'm saying is the expected value of x is expected value of x condition on y is a random variable, can take different values, and depending on that, the expected value of x over condition on y changes. So think of this as y. So basically you think of this as a function of, if I look at a conditional expectation conditioning on knowing what the value of your random variable y is, basically your answer is just some function of y. And if all I'm saying is I wanted the expectation of that g of y. Taking expectation of g of y is summation over all y's, g of little y multiplied with the probability that y equals little y. Or maybe I should write it as the p bar of y. In the continuous case, what I'm saying is that the expectation of x is just the integral of this function, g of y, so if you find the conditional expectation, then you can use that to calculate the unconditional expectation. The way you do it is you take the conditional expectation, weight it with this probability, and integrate. One example and then I'll answer today. Here's an example where we're going to calculate the conditional expectations, and then we'll use that to calculate the absolute expectation. And let's do a discrete case example. Suppose x and y have joint probability mass function like you to calculate, find the value of x for all y values, and so what are your possible y values? The only y values that occur with positive probability are y equals 0, 3, and 4. So for y equals 0, 3, and 4. So calculate this conditional expectation for y equals 0, for y equals 3, and y equals 4. So when you find that out, we list this. These first. So we have to first calculate those, and once we've calculated these, then the expected value of x would just be 4. It would just be this. Nice. So each of these values weighted with the probability that y takes that number. Right, so let's, so you know all the formulas that you need to calculate this. First step, to calculate conditional expectations, you need the conditional probability mass functions. So find the conditional probability mass functions first. How do you find the conditional probability mass functions? They are the joint probability mass functions divided by the probability mass function for y. So actually, first step is finding probability mass functions for y. So that would be py of 0, py of 3, py of 4. Go ahead and calculate that. And then with this example, we are done for today. Next class, we go over more problems calculating conditional and unconditional expectations. So, and then we will get this. What should the possible x values be? X only takes values 5 and 8. 8, yes. Alright, so what is py of 0? So you keep y fixed as 0, x can take value. So it's this plus this, right? 7 plus 3 7. What's the probability that y equals 3? Y equals 3 and x equals 5, or y equals, oh yeah, okay, that's the only way y can be 3. So that's 1, 7. What's the probability y equals 4? Y equals 4 and x equals 5, or y equals 4 and x equals 8? So I add up these two probabilities. That gives me the probability that y takes the value of 4. So I have the probabilities for y. Remember that this is how we get you add up over all your x values that you can do. So this is going to be 5 times pxy. By definition, this is the joint probability of 5 times 0 divided by 0, 8. Probability that x equals 5 and y equals 0 is 1/7 over py of 0 is 7 plus 8 times 8, 0. 3 sevenths divided by py of 0 is 4 sevens cancel out, so you get 5 plus 8. Okay. 4 plus 3, 24 over 4, 29 over 11. Go ahead and calculate the others as well.
Wouldn't it just be when x is 5?
Yeah. So the other one would be 0. So yeah, just be x equal when y equals 3. Yeah.
3.
Yeah.
Oh, is that an 8 after it or no? No, I'm sorry, over the sum and x is
Yeah. So I say 8, but then this would be 0 when x is 8.
when the probability. Okay.
So then this case is very simple. You only have to consider the case when x is 5, because as you pointed out, when x is 8, this is 0. Alright, so it's just going to be, so this is just the probability of, what is it, 5 comma 3, 5 comma 3, 5, that's probability 5, 3, so plus 1/7. Probability that y takes the value 3 is 1/7. This is 5. And the last one is 5 times the probability of 5 comma 4. plus 1/7 divided by the probability that y takes the value 4, 2/7 plus 8 times the probability of having 8, 4, that's this, 1/7, and divided by probability y equals 2/7. So you have 5, 8, 2, 13. So you've calculated your conditional expectations, and now the expectation of x is just the weighted condition expectation. You just take the average of the condition expectations. So it's 29/4 times the probability that y equals 4. Oh, sorry, that y equals 0, sorry. 29/4 probability y equals 0, which is 4/7, plus this expectation, that is 5 times the probability that y equals 3, which is 1/7, plus 13/2 times the probability that y equals 4, and that's 2/7. Calculate that, you get 29 plus 5 plus 13 divided by 7. What do we have? We have 29 plus 18. Is that 47? 14, 8. So these are your conditional expectations. This is your unconditional expectation of x. So your unconditional expectation is just a weighted average of your conditional expectations. You weight it with the probability that y takes these values. I mean, an example of this would be, say, you have 3 possible ways of producing something, and each has a different cost, expected cost. Okay, you say you choose, you produce this in the first way with some probability, the second way with some probability. You decide to use the third method of production with some other probability. And then you can look at your expected cost. It would be the expected cost if you had chosen this, the first method of production, weighted with the probability that you've chosen that method of production, plus the expected cost of the other method of production, times the probability of actually choosing that method of production. So you see, it kind of makes sense. So the expected value should just be the expected value for each of the possibilities. Okay? Depending on your choice of y, what was the expected value of x, and what was the probability of you choosing this y. Okay, so we'll do a couple more problems on Wednesday, and then move on to